All right, so last time, a couple classes ago, we looked at electric forces and how they're related. We talked about the electrostatic force being represented by that Fe, still measured in newtons. We talked about the charges of the particles being involved, either Q1 or Q2, measured in coulombs, and then we had our distance that the two objects were separated, measured in meters. So that's the first part about it. Now what we have to look at is what we call an electric field. So your electric fields were first came up with by Michael Faraday, and really what he looked at was how a force is acted over a distance. So what he was looking at is basically like with what y'all did with the tape, where you push the two pieces of tape together and they either attracted or repelled more. He was looking at that to see how the force is going to act over a distance. As you increase the force, what happens to the distance? As you decrease the distance, what happens to the force? And vice versa. So really what we're looking at is with an electric field is it's basically the space around every single electric charge. So whether it's a proton or an electron or some other random charge, all of it's going to have this area around it where it's an electric field. So the force that we're looking at, that one charge exerts on another one, is looking at the interaction between the two's electric field. So basically when you bring one charge near another charge, each charge has its own electric field, and so what we're looking at is how those two electric fields are going to interact with one another, okay? With all of these, we're never talking about the two objects coming into contact. So just like we did with the tape, you didn't actually ever touch the two pieces of tape. You just brought them close together, and then you saw either that repelling or that attracting force from there. Just like electric force and displacement, your electric field is a vector, so it has to have both magnitude and direction. So with your electric fields, we're going to look at which way they're going and the size of it. Okay. Now with this unit, it's a little weird. How you determine the direction is a little bit different than what we've done in the past. For those of you that don't like math, don't worry. This one is not math based. For the direction and the magnitude will be. So math for part of it you just have to know. So your magnitude of your electric field or your electric field strength is looked at basically based on the charge. So what charge is located within that electric field? The bigger the charge, the bigger the electric field. Okay, how we test to see the strength of an electric field is we use something called the positive test charge test. And so what that is, they actually take some positive charge and they put it inside an electric field and they see what happens to it. Does it attract? Does it repel? Does it move fast? Does it move slow? And all of those things can tell them about the strength of the electric field that it's being induced in. Now, the big thing about it is that it has to be really, 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 really small. Okay, we don't want to change it. We don't want to alter your electric field. We don't want to mess it up. So we bring in this really, 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 really small particle so that way we can just see how it interacts and gather our data that we need there, and then you can remove the charge and it still goes back to the way it was. So we don't want to change it, we just want to see how it's going to be affected so that way we can measure the strength of it. Okay, wherever the force is on a test charge is the largest, that means that the field is going to be the strongest. So if it's really getting a strong attraction or a strong repulsion, remember if they're like charges, they're going to repel, opposites are going to attract. So really you're looking to see, is that force, whether it's a repulsive or attractive, if it's a really, 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 really big force, that means your field is the strongest. Okay, wherever your force on your test charge is small, so you don't see much repulsion, much attraction, that means that your field is going to be a lot smaller. Okay, and then we measure electric fields in newtons per coulomb, or N/C, newtons per coulomb. Okay, when we're talking about the direction of your electric field, what you do is you're going to look to see whether your field is, if your charge producing the field is positive or negative. If the field is being produced by a positive charge, that means that your field lines are going to point away from the particle. So if you look at this picture here in the middle, you have your positive particle in the middle, and then you have all these lines, and the arrows point away from the positive particle. Okay, you have another one down here at the bottom of the screen. That way you can just see another example of it. Okay, sorry about my phone going off. The next one that you have then is if it's a negative charge. Okay, if it's a negative charge, the only thing that's going to be different is that your electric fields are going to go towards the particle. So all of your arrows are going to go in towards the particle instead of away from it. Okay, so we don't have to worry about north, south, east, west, up, down. All you're looking at is does it go towards the particle or away. Away is positive, towards is negative. Okay, so just remember that however you want to do that. Okay, you'll also notice that the field lines don't cross. Make them little circles around them. Okay, if you want to, so that's how we figure out the direction. If you want to figure out the magnitude of the electric field strength, then you have to use the equation. E equals F over Q. Okay, or you can use the equation E equals KQ over R squared. In your equation, E equals F over Q, you're going to have a force acting on a charge. If you're using the second one, then you have two charges. Okay, so just look through the problem, write down your givens, and then that'll tell you which equation you're going to use. E is your E field, your electric field strength. F is your force. Q is going to be your charge. Okay, and then R is going to be the distance between them, just like they were for the FE equals KQ1 Q2 over R squared equation. Okay, when you're looking at your electric field strength, the first thing that it depends on is the charge creating the field. So the bigger the charge that's creating the field is, the bigger the electric field is going to be. Okay, the other thing that's going to impact it is the distance. So depending upon how far apart they are. If you notice that distance is in the denominator again, so that means they're going to be inversely related. So as you increase the distance, your electric field is going to get smaller, and as your distance decreases, your electric field is going to increase. So your electric field is inversely related to your distance, just like the electrostatic force was. Okay, your electric field lines, so we kind of talked about them a little bit earlier. Looking at drawing those field lines, remember positive particle, it always goes away. Negative, it always goes towards. So we mentioned earlier about the force and what that means, that wherever the field is the strongest, the force is the largest. So wherever you see where the field is strong, where you get that much stronger force, that means that your electric field lines are going to be a lot closer together. Wherever your electric field is really weak, that means your lines are going to be further apart. Okay, so you're just kind of looking at it to see if the lines are close together, then that means they're stronger force or stronger field, further apart, weaker. Okay, so if you look down here on like this bottom picture, you see these field lines are much closer here than they are over here on this side. Okay, notice that they're all going away from the object since it's a positive particle. Your field is going to be much stronger over here than it is over here, just because of how close the field lines are together. Okay. All right, when you go to draw them, you are going to have to know how to draw them. So these are your rules. The first thing is that your lines always begin on the positive charge and end on the negative. So if you were to connect them, so just remember the arrows go away from the positive and towards the negative. And then you have to come up with a ratio. So sometimes we deal with really big charges. Sometimes we deal with really small charges. If you think back to before, we talked about the charge of a proton or the charge of an electron being 1.6 times 10 to the negative 19th coulombs. How are you going to draw that? Okay, so what you do is you create a ratio. Okay, and the number of lines drawn has to be proportional to the magnitude of the charge. So if one object has 2 protons, one object has 1 electron, then the 2 proton one just has to have double the amount of lines as the other one. Okay, so here you have that imitation, that picture over here. You have a 2 plus charge and a negative 1 over here. So it means this 2 plus 1 has to have double the amount of field lines that this object has. Okay, as long as they're double, then you're fine. Okay, and then the last part is that they cannot crisscross each other. So you can't like move one of these field lines so it looks like this. Okay, they cannot cross each other, even if you could do it so that way they're still pointing at the object a little bit, you cannot cross them. Okay, so nothing like this. They all have to be pointing towards the object. If they're negative, cross them, and they cannot cross each other. Okay, the next thing we look at is when we're drawing these is this idea of an electric dipole. An electric dipole is what you get when you have two equal but opposite charges. Okay, so that means you have a positive and a negative that they're both the same. It could be a proton and electron. One could be +5, one could be -5. And what happens is that all of your field lines will connect. So if positive and negative want to be together, they're attracted towards each other. So that means what you're going to end up with are the field lines leaving the positive one and going straight into the negative one. Okay, so all of these lines, if you follow another one, it leaves the positive and it goes towards the negative. If you count all the lines are on the negative and all the lines are on the positive, they would have the exact same amount of lines since they have equal amounts of charge. Okay, and an electric dipole is only there when you have equal and opposite. Okay, and again, just like before, wherever you see the field lines really, really close together, that means that you're going to have a stronger electric field. So you have a stronger electric field in the middle right here than you do when you're out here on the outside. All right, so here's what the field lines look like if you have equal positive charges. So that means you have the same amount of lines on the two of them. Okay, together. But you'll notice that they're bending away from each other. Okay, completely bending away from one another. Okay, so the field lines go away from the positive charges, so all the arrows go out. And then they're going to bend away from each other because they're going to be repelling. So basically you end up with this space in the middle where neither one will ever touch. Okay, if they're unequal and opposite charges, okay, then that means that you'll connect all of the ones that you can, and then whichever charge has more, then that one will just have more lines. So if you look, you have 1, 2, 3, 4, 5, 6 negative lines. Okay, on this one. This one is double the charge. So if you look how many lines are touching that one, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, we don't know what the charges are, but we can see based on counting the lines, the negative is half the size of the positive. Okay, or the positive is double. So connect the lines that you can. Always go away from the positive towards the negative. And then the ones that don't connect, you kind of just draw them out on this side. Here's what a more complicated one looks like. You're never going to see anything that crazy. So, all right, well, I'm going to stop with that one for this video. So that was just on electric field. When I come back on Wednesday, we'll review and practice drawing these some more for you.